Do we have any questions from gases? Was it gases we did? Yeah. Yeah.
So the homework was going into like phase changes.
Uh-huh.
I'm not sure if we had covered that. Really. It was like.
Okay, what kind of problems did it give you?
Let me see. Hold on. And like I could watch the video and like once to get the answer.
No, let's make sure we got it. Any other questions while we're waiting? You got it down? Good. Go for it.
Okay, so it says the heat of fusion of acetic acid is 45.9 calories per gram.
45.9? Okay.
How much heat in kilocalories is required to melt 3.05 moles of the solid acetic acid?
How many moles?
3.05.
3.05 moles of what acid?
Solid acetic acid. So how much heat in kilocalories is required to melt 3.05 moles of the solid acetic acid?
All right. Yeah, we didn't go over this. But let's see what we can do. We have, and so, ladies and gents, this is where dimensional analysis will really help. We have a unit of calories per gram, and we want kilocalories. We can convert calories into kilocalories, just like any anything, right? Does that make sense to everybody? Okay. We have grams in here, and we have moles, so what should we do? Yes. Convert moles into grams. So we have 3.05 moles of HC2H3O2. And does it tell you what acetic acid is? Does it tell you the chemical formula? And we didn't learn about how to name acids in this class, did we? We did not, right? So, on homework, I will never have you do this for an exam, but on homework, Google knows. Just look at what's the chemical formula for acetic acid, and it'll give you. It might give you something like this: CH3COOH. But it's the same as that, right? If we look for the molar mass, it's going to be the same. So then you convert moles into grams using the molar mass. So then we have grams of acetic acid. And then you multiply by 45.9 calories per gram. And grams goes away. And then you convert calories into kilocalories. Does that make sense?
I figured it was some dimensional analysis.
So that's the beauty of dimensional analysis, guys. In the problem-solving strategy, you can solve any problem. I mean, there's some things that you have to know before you can solve, but for the most part, you should be able to figure any of this stuff out. Does that make sense? And so that's talking about turning solid acetic acid into a liquid, right? To melt it. Or is it the other way around? Yeah. But anyway. Any other questions? All right, let's move on to chapter 9. So chapter 9, there's not a whole lot in chapter 9. So we have 2 days to complete chapter 9 and do any review we need. And then we'll have an exam on, I think you can schedule it to take on Monday is the last day. But I don't like it. I'm gonna call them and ask them if they can change it to be Wednesday. They're closed on Thursday and Friday because Thursday's a holiday. No school on Thursday. Okay. Yeah, next Thursday. Yep. Yes, next Thursday. Not this coming Thursday. So I will talk to the testing center and see if they can bump it up, and you can take it up until Wednesday. That okay for everybody? All right. Anything else before we go on? All right. So chapter 9 is about solutions and concentrations. Solutions. Anybody know what a solution is? We're not talking about the answer to a math problem. Okay. What's a solution?
They consist of 2 or more parts.
Okay, it is.
Often dissolved in liquid.
Perfect. Okay. So 2 parts. Two substances put together. What do we call that? What'd you say, Emma? Mixture. Yeah, this is a mixture. And specifically, solutions are homogeneous mixtures. Yes. Homogeneous mixtures. So is it just all homogeneous mixtures or solutions? Okay. Does it have to be a liquid to be a solution? What kind of, you're saying no, all homogeneous mixtures are not solutions. What kind are not, Alex?
I don't know. I can't think of an example. It just doesn't feel right.
Okay. Now, there are some tricky ones that are not homogeneous, they're heterogeneous, like blood, for example. Blood, if you just look at blood, it looks like homogeneous, right? But it has small particles in there that will just settle out. And so it's not really homogeneous, so we don't call blood a solution. And there's a few other things. There's colloids and extension or suspensions that are heterogeneous mixtures, but they look like homogeneous mixtures. Okay. But if it's a true homogeneous mixture, basically it's a solution. And I don't know everything. Maybe there's an example where it's not true, but in my mind, in my experience, if it's homogeneous, it's a solution.
Okay, so then, like, why would a cake not be a solution? That's why I'm getting tripped up.
Maybe. Okay. It could be. Definitely could be. And I wouldn't see why it still wouldn't be a solution.
Right?
But like you mentioned in the definition, 2 things that are mostly liquid, right? Most solutions we deal with in chemistry will be liquid. They will be.
Read that like straight out of the notes though, so.
And yeah. Anyway, it's okay. We can go with that for sure. Okay. But anyway, if it's a homogeneous mixture, basically it's a solution. So we could have solid liquids and gases, gas solutions, solid liquids and gas solutions. So let's think of examples. We can think of a million examples of liquid solutions, right? What's an example of a solid solution? We talked about when we talked about homogeneous mixtures. Yeah, like a metal alloy, like steel, for example, right? Steel is a solution of carbon, mostly iron, right? Okay, and a gas. What's a solution of gas? Air. Right? Does that make sense to everybody? So, like Alex mentioned, there's two parts to a solution. You have to have at least two substances. And you can have more than two, kind of like soda, for example. Is soda a solution? Yeah, it's a solution of what? Water, carbon dioxide gas, sugar, flavorings, whatever, right? So, but it has to have at least two. That's what a mixture is, okay? And the two components specifically we use for solutions are solutes. And the solute is the component that's dissolved in the solution. But back to that cake example, we probably don't really call cake a solution, right? Unless it's somebody's birthday, and that's a good solution. But okay. But anyway,
It
yeah.
seems like there might be a distinction made about particle size, whether it's considered a solution or not, because it says that solutions.
Yeah,
Particles the size of a typical ion or small molecule, 0.1 to 2 nanometers in diameter. So
And I went through that, and it also says the ones that aren't, if it has bigger particle size, we call it a colloid or a suspension. And a colloid or suspension are heterogeneous mixtures. But so great, so anyway, not a big deal, not a big deal. But we're not going to get into the nitty gritty here. So, but yeah. Is that what it says there?
yeah, it does. It does give two examples of colloids that are homogeneous, milk and mayonnaise.
So
Homogeneous ones.
I would say that they're not, because they both settle, unless you homogenize the milk, right?
And settling makes it not a solution? Sorry.
What?
Does settling make it not a solution? Or a
Yeah, if it settles out, that means they're. I mean, you can mix it up and it looks like homogeneous, right? But as it settles, homogeneous mixtures don't settle out. But anyway, again, not a huge deal. So I'm not gonna. Well, I'm gonna try to get this guy. I remember when I teach 1010. It seems like the professor that set the 1010 course up, and he made the test and stuff, and he likes to do stuff like that. What? But anyway, and Mary Alvarez is the one that did this exam, and they're great. So for the most part, but like I said, I'm on your team. I'm on your side. If there's a one that's just, come on, that's too tricky too, you know. I don't think that's especially for this class. No, maybe for a class where you're going to engineering for like 1210 or something. Maybe they're a little bit more that way. But for this class, I think we should be straightforward. Any other questions on that? All right. So a solute is the component dissolved, and the other part in the mixture is the solvent. This is the component that dissolves. or the dissolver. A component that dissolves the solute. You guys familiar with the word solvent? Well, I learned that word when I was 15. I don't know if I told you this story. I think I might have told my other class, and I always get confused which class I told what. So if I told you, it's like, oh, come on, here he goes again. Then just stop me, okay? But when I was 15, I was working at a print shop. And, well, I was just a young kid, so I doing all the grunt work, sweeping floors, taking out the garbage, whatever, right? And then my boss says, hey, do you want to learn how to use the printing press? I was like, oh, yeah, that'd be cool, right? Big, has to be 18 to use it. But he said, yeah, let's show you how to use this. And, well, he showed me the grunt part of it first, because you have to clean it out. Because if you leave the ink in the press, it hardens the rollers, then you have to get new rollers, and that's thousands of dollars, you know? So he says, okay, let me teach you how to clean this press out. And, well, you put this little scraper in there up to the rollers, crank it in, and the rollers turn, and it kind of takes the ink off. But it doesn't take a lot of ink off until you put some, we call it solvent, right? And it probably has a better chemical name. I'm not sure what we used. I was just 15. But, so he says, okay, we pour the solvent in, and it kind of dissolves the ink, and then it comes out, and it cleans the press out. And anyway, we had this little squeeze bottle would squirt in the press, and we had a little 5-gallon bucket with lid on it and stuff that would have, in case that little bottle got empty, right? Well, when that bucket got empty, well, we had a drum back in the back. And he says, okay, this bucket's empty. Do you want to go fill it up? Do you know how to siphon? And I'm thinking 15-year-old, they know everything, right? And so I think, yeah, I know how to siphon, right? And so I go, yeah, where's the hose? So I grab the hose, go out there, and then the experience starts. Because this is pretty volatile stuff. And so I'm trying to do this, and it didn't work the first time. Or the second or third or fourth time, it's like, well, I'm out here dying. In the meantime, my boss is thinking, where is that kid? So he goes out there and he's, whoa, stop, what are you doing? And he gave me my first physics lesson. I should have knew this. We do this all the time, right? We get our straw, we put it in our drink, right? That's all we need to do. Throw it in there, put your thumb on it, there you go. But I learned the hard way. But anyway, that's my first experience with solvents. What are solvents? Dissolvers, right? It's the majority of the solution, and it's what dissolves the solute. So we'll just say this is the majority, and the solute is the minority.
Is that an absolute?
What?
Like, is the solvent always gonna be the majority?
I was just about ready to say, no, there's always weird things, like, for example, rubbing alcohol. Rubbing alcohol, now, normally we say the solvent is water, especially in chemistry. We use water as the universal solvent, but with isopropyl alcohol, rubbing alcohol, it is mostly isopropyl alcohol, a little bit of water. It's like, if you look at the bottle, it's 70 or 90% alcohol, right? So in that case, if we stick to this, then alcohol will be the solvent. Really, they dissolve into each other. So, but again, we're not going to make a big fit about the difference, right? But in general, yeah, this is what it is. And would it be okay to say the isopropyl alcohol is a solvent? Sure. It dissolves the water dissolves it. They're both covalent compounds. So in ionic compounds, what happens when it dissolves? It dissociates, right? Breaks apart, and then the water solvates the different particles, surrounds it, and then it's dissolved. Well, what happens in covalent compound when you throw sugar in water? Does sugar break apart? No, sugar is a covalent compound, so it stays there. But what makes it be able to dissolve in water? Does anybody remember? Like dissolves like, right? And so how is sugar like water? They are both covalent compounds, but that doesn't make it, because oil is also a covalent compound. It doesn't dissolve in water. What do we mean when we say like dissolves like?
Oh, polar.
Yeah, they're both polar. So sugar's a polar molecule and water's a polar molecule, so sugar dissolves in water. Make sense? But in this case, water can't dissolve in sugar, right? So with rubbing alcohol, it's a little bit of a different thing. We good? Okay, gases can also dissolve in water. And we know that, especially if we drink soda. We have carbon dioxide dissolved in water, make carbonated water. Okay. All right, so let's show what's going on when things dissolve in the microscopic level. Okay. So let's zoom way in and see what's going on. Did I already show you this a little bit, maybe? Okay. So if we have a container of water and we throw salt in it, for example, then the sodium ion breaks apart from the chloride ion, yeah? And what happens? Well, why does it break apart? It breaks apart because it's more favorable to be attracted to the water molecules than it is to each other. And what makes it that way? Maybe because these guys are highly reactive components, right? And so if they're highly, we kind of talked about the solubility chart, which ones are and which ones are not, right? But so what happens is sodium is a positively charged ion. And what part of the water surrounds sodium? The oxygen or the hydrogen? The oxygen, because the oxygen is partially negative. It's not negative, but it's more electronegative, so it's going to have more of the negative charge on it, yeah? So we have our oxygen, flip the water like that, and we get something like this. And when it completely surrounds us, and I'm not drawing this exactly how it is, there's probably more than just 4. There's probably 6 is my guess, okay? Because of the structure of water. But it's going to surround it, and then once it completely surrounds it, it's dissolved. And then you have chlorine. What side attracts to the chlorine? The hydrogen. So it's going to be flipped around. Is it going to look just like this? No. And this process is called solvation. Process where the solvent surrounds the dissociated ions, and then it's dissolved. Now what happens if you keep pouring salt in the water? It'll stop dissolving, it'll stop solvating, right? And the reason is because, well, we have too many particles and not enough particles of water to completely surround it, okay? Well, kind of. At a given temperature anyway, right? But we increase the temperature or pressure and we can dissolve more. Does that make sense?
What is that just because if that makes more movement, more Brownian movement?
Yeah.
And then the
Yep.
particles can interact more, okay.
More collisions, we talked about collision theory, more collisions, it's gonna have, and it's not reacting with it, but it's just, interacting with it, yeah. Okay, this is how, yeah, question, Rebecca.
How many hydrogens will be like around chloride? Because it usually wants to be like full.
Yeah, is it gonna be just like this?
No, but I'm.
No, it's probably gonna try to do it to where, cause there's electrons going on and they're repelling each other, so it's gonna, but exactly how it goes, how it does it, that's not our interest here. But it might do something like this, right? But then, but it's still gonna surround it. Good? Great question. Why don't you think on that? Sorry, guys. I'll be right back.
Because, like, you're not creating that new molecule, right?
Right. Right, you're not creating like CLH8 or something.
Exactly.
Like, it's not a new compound.
Yeah, so I think it's like the kind of magnets that you're kind of like different.
Right. That's kind of how that works. Yeah, I wonder. I don't know, cause wait, no, hydrogen bonding only occurs between chlorine, oxygen, and nitrogen. I don't think it happens with chlorine. I don't think the electrolytes into this very long rainfall add up to curvature to chlorine. I think it's only that chlorine oxygen.
This makes sense.
You're kind of biased, so.
This is like
I mean, it is in
my
the R,
exposure, so
but
it's
it's
kind
gonna
of
be.
watch
Well, he's a guy. Well, she's a guy. He's a guy. Do you think it's retonic?
Well, intermolecular force.
Okay. Well, I'm gonna say, yeah.
Because he said it's not like a six. But I don't know why.
We good on solvation process for ionic compounds?
You had a really good question.
Yeah.
Yeah, this might be another, like, this might be outside of the scope of this specific class, but
Okay.
we were curious about what the actual specific process is where the hydrogens can attach to the chlorine. We were talking about whether it's intermolecular forces or whether it's an actual bond that's forming, or if there's any bond that forms at all.
Good, yeah.
What is the interaction that's actually happening?
What do you think? Is it a bond or is it intermolecular force?
Well, from what I remember about intermolecular forces, hydrogen bonding only occurs between hydrogen and fluorine, oxygen, and nitrogen.
Uh-huh.
So it wouldn't happen with chlorine.
So it's not hydrogen bonding,
It's ionic.
it's probably a dipole.
Right.
Right.
Partial positives and partial negatives.
So it's not a partial positive, so sodium is not a partial positive, but it still is kind of the same, right? So ionic compounds, we don't call polar compounds, we just call them ionic. But are they polar? Do they have a positive side and a negative side? And can you draw a line that Yeah. So, yeah, it's an intermolecular force. It's not a bond. If it were a bond, you'd have a transfer of energy, and then you'd have a chemical reaction or a chemical change. And a dissolving process is a physical process, physical change.
Not a chemical change.
Yep. And how do we know?
Because the molecules stay the same.
Because you taste salt water, and it tastes like salt and water, right? It doesn't change what it is. You evaporate the water, and it's now salt again. Good? Great question. So let's see. Just like we talked about sugar and water, I'm not going to draw sugar because, well, I'll try. And it's not exact, so don't treat this as scripture here. Sorry. If we have sorry. Anybody gonna take organic chemistry? When I took organic chemistry, there's drawings like this all over the place. You just draw and draw and draw, because that was a tough course, and so I studied more for that course than I did any other course, but it paid off. So anyway, so here's a compound, and these right here, these are all carbons. All these points right here, and we just draw it this way because there's this law of carbons and hydrogen, and every one of these carbon has hydrogens bonded to it. But in sugar, there's also a bunch of oxygens bonded to it. Exactly how many? Well, C12H22O11. So I'm not counting these, I'm just drawing, okay? And right here,
How many oxygen? 2? 4?
there's 11 of them. Okay, and you don't have to know that, but so it's these oxygens that make this a polar molecule, because if it's just carbon and hydrogen, it's nonpolar, right? So then you get water that, I'm not going to draw all these, that does that around the oxygen, and all the way around until it's solvated. So it's the same process, still solvation, but they don't dissociate. Does that make sense? And that's why like dissolves like, because we have that intermolecular attraction.
So you put like oil in water and shake it up. Would that be like a suspension because they're not actually like interacting with each other?
Yeah.
Okay.
Yep. You shake it up and it looks like a little bit like homogeneous, right? But then it just whoop, the oil will just go up.
Right. Okay.
Less density, and yeah. And I don't know if we'd call that a suspension, but yeah. All right, does that make sense so far, how things dissolve? Yeah, Lucas.
I have a silly question, but I wanted to take a chance on this. So, when we have big, like, hydrocarbon compounds, they're all like nonpolar, right?
Mhm.
There's no kind of dissolving that's happening there. But earlier in the example where you're showing how salt basically gets surrounded by the particles of water,
Uh-huh.
you were showing how with the chlorine, the hydrogen sides come in closer to the chlorine because it's partially negative, right?
Yep.
And then you were showing with the sodium how the oxygen side is facing them because they're flipped, right? So the charges
Mhm.
attract each other. So why can't that happen with a strictly hydrocarbon compound where the oxygen side of the water comes and attaches to the hydrogens?
Good question. Because there is a slight difference, right? So if you take carbon and hydrogen, so that this electronegativity value for carbon is 2.5 and this is 2.1. So 0.4. There is a slight difference, right? So why doesn't water surround this? It's because it's more favorable for the intermolecular force of water to water. That's a stronger attraction, and so that's going to happen and not around that guy. Does that make sense? And that leads into what I was going to talk to next, so perfect. That was not a silly question.
Our chemistry is so good.
Yeah. If you want to call it that. No.
Thanks, Chad.
All right, so why don't all ionic compounds dissolve in water? We had that solubility chart, and some are insoluble. They're still made of positives and negatives, so why is it that they don't all dissolve in water? And it's
It's because the charges on the metals are stronger, so they tend towards, they stay attracted to those.
Yeah.
instead of the water molecules.
it's more favorable to stay together than to break apart and hook up to a bunch of water molecules. And here's an analogy that might, because I think we can all understand this a little bit better. I tried making a AI make this image for me. They couldn't do it. I asked them a couple different ways, and they just gave me a jar of marbles, and that didn't really help. And so I kind of put this together. It took so long, so I hope you guys are.
Really appreciate it.
But in here we got a bunch of marbles, but we also have some magnetic spheres, right? You have a bunch of marbles and you throw one magnetic sphere, you won't even notice anything. It'll just go around wherever, right? You throw two in, what'll happen? It'll hook to that. It won't need to be just around the other marbles, it just wants to be attracted to that one. So that's kind of what happens in ionic compounds that are not or are insoluble in water. They want to stay attracted to each other, kind of like those magnets, rather than break apart and then kind of interact with the marbles. Does that make sense? Any questions on that idea? All right, and there's a few terms I want you to know. If we take rubbing alcohol, for example, you can mix. We had a 70% solution. We have 90% solution. Can you have a 2% solution? Sure. Can you have 100%, 99% solution? Yeah. As soon as you have 100%, then it's not a solution, right? Okay. It's just isopropyl alcohol. But a solution where you can have a solution in any proportion, where things will dissolve in any proportions, then we call that a miscible solution.
Is that MISC or
MISC, yeah. A miscible solution is where the solute and solvent dissolve in any proportion. And the opposite of that is, yeah, something like that. Immiscible, but it's where they do not dissolve in any proportion. So an example of miscible is C3H8O and water. So that's rubbing alcohol. If you put those together, but an immiscible solution is where the solute does not dissolve in any proportions. What's an example of that?
Solution? Sorry, is it?
Two substances that just do not mix. Oil and water.
Immiscible solution?
What?
How you can read this?
Oh, sorry. The solute does not dissolve in any proportion.
The first one.
Okay.
Immiscible solution.
Solute will dissolve in any proportion.
No, the first one.
Miscible,
No, down. Immiscible solution.
immiscible solution. Put a M in front of it, it makes it opposite, right? I don't know.
Impossible.
Yeah, possible and impossible. Good. So oil and water is an example of an immiscible solution. And they don't mix because oil is nonpolar and water is polar. Kind of like the marble situation.
Immiscible.
Does that make sense to everybody? All right. So how do we increase solubility? So you add salt in, it'll dissolve until you add a little bit too much. So how do you increase that solubility we talked about? Okay, you can add more water,
Oh, more temperature.
but if we have a certain amount of water, so you can only dissolve a certain amount of salt at a certain temperature and pressure. So if you increase the temperature and pressure, you'll increase solubility. Does that make sense? Now, sorry, it lost. Oh yeah, so why is that?
More space for things to like, no,
More energy, so
vegetation.
less space between molecules because they're moving faster if they're hotter, or if you increase the pressure, they're colliding into each other more often, right?
More collisions.
But really what happens, if we have things moving faster and faster and faster, what do you think? Is that going to be more order or less order? Or more disorder or less disorder? Let's talk about disorder. More disorder, right? If you have more disorder, then we can talk about delta G equals delta. Oh, not again. Okay. So, but this is what helps us to know what's going on and how we can change things. Okay. So if we increase the temperature, make that bigger, that's going to change whether it's spontaneous or non-spontaneous, right? It won't change whether it's exothermic or endothermic. And the process of dissolving is not either one of those. It's just a physical process. But it'll still tell us whether it's spontaneous or non-spontaneous. Does that make sense to everybody? So at a certain point, you can add a lot of solute in it, but then after a while, you might have to stir it up to get it to dissolve, right? Or shake it up or whatever, okay? So a gas phase has higher entropy, right? And so if you want to dissolve gas in water, we got to increase that pressure to get it to force it in. Does that make sense? To have it even more, more entropy. So this kind of helps us tie it in also to Le Chatelier's principle, right? So if we increase the pressure, it's going to allow those molecules, those gas molecules, to collide more often and to make more of the product, or vice versa. Good? All right, I think we talked about this, but maybe we didn't. It might have been my 1210 class. So there are substances that can dissolve both polar and nonpolar, like soap. We did talk about this?
No,
Did-
I just know that.
Did we talk about this, guys?
We talked about
We have talked
Okay. So, did I try drawing this for you? And it was like, oh, that looked goofy. 'Cause I'm not the best artist, but I'm gonna pull up this image because it's a little bit nicer to look at. Okay, so you have this guy right here. That is, well, we can say what it looks like, but it has a polar head and a non-polar tail. Okay, and well, that's why oil is dissolved in the non-polar section, right? And then you got the water on the outside that kind of solvates the whole thing and kind of just pushes it out. That kind of makes sense? Okay. So, yeah, it's nice to say just like dissolves like, but you have some components that are kind of both, that kind of a equalizer or whatever.
So the oil's not really dissolved, it's just like.
It kind of hooks onto it.
Right.
There's an intermolecular force that hooks onto it, and then the water pushes it out. So it doesn't dissolve in the water. It dissolves in the soap,
Right.
and then the soap dissolves in the water-ish, kind of. Does that make sense?
Yeah.
But soap is mostly non-polar. That's why when you get soap on your hand, it's kind of a little slippery, right? All right, last thing on solutions, and then we'll, we're going quick. Are we understanding this?
Yeah.
That's very,
Okay? Because on Thursday, because if we finish this material today, then we just have a review session. So I gave you guys the study guide, right? Okay, so come with questions next time. That last review was the best review I've ever had in 1110 class. Because most of the time people don't have questions, and then, well, if you don't have any questions, I don't know what you need, right? So go through that, study with that, come with questions, and we'll have a good review again. When's your exam?
Monday.
Monday? So ours is Monday as well, but I'm going to push it out to see if I can get you till Wednesday. If just because you have to schedule it in the testing center. When I did this during the fall and the spring, then we just did it in class, and so it was just on a certain day. But you're going to come anyway, and so it was okay. But since it's at a testing center, you have to reschedule your whole schedule. It's like, that was the only time I had for this class, right? So that's why I'm giving you a little bit more time. All right, so just a few more terms. And we kind of talked about it a little bit, but if we have an unsaturated solution, that's when we put a little bit of salt in there and it dissolves. Can we put more in?
Yes.
Yes. So it's a solution where not the maximum amount of solute is dissolved at a given temperature and pressure. Okay? So concentration of solute is less than maximum at a given temperature and pressure. less than max. That means we can still dissolve more if we want. So most solutions are going to be unsaturated.
Less than maximum of.
Maximum, less than maximum at a given temperature and pressure. And the saturated solution is when it's at the maximum. Concentration of solute is at maximum for a given temperature and pressure. Is that it? Also have a super saturated. What does that mean? More than the max. What? More than the max? Over dissolves. So how can you reach super saturated? You increase the temperature and pressure, then it's a different temperature and pressure, right?
Bring it back down.
Then you let it cool at room temperature. You don't put it in the freezer. You just let it cool slowly, and it'll still stay dissolved. And the cool, I wish I had this actual demonstration for you, but because it's pretty cool. Guess I could. I don't get internet on this, so I can't look it up, but it's called sodium acetate in water. So just type in a supersaturated solution of sodium acetate in water, and you touch it after it's cooled down, and you touch it, or put another salt crystal in there, and it'll just crystallize right in front of your eyes. Pretty cool. You guys ever see that with water? You put, because you can have liquid water at less than 0 degrees Celsius, right? As long as it's not disturbed. If it's undisturbed, then you grab the bottle of water out of the fridge or out of the freezer, whatever. It's like, it's not frozen. Then you shake it or pour it out, and it'll just solidify. Okay? Kind of the same idea, not exactly. It's not talking about it's not a super saturated solution, but. All right, any questions on solutions? We still have 20 minutes before our break. Let's go over some of these examples on this worksheet. Oh, let's talk about section 1. Section 1 is kind of a review, but it relates to this. Okay? So which of the following atoms or molecules will be more likely to form a solution with water, and which will form with C8H18, which is gasoline? You don't have to know that it's gasoline, right? So what's the difference between H2O and C8H18? One's polar, one's nonpolar. So how do we determine which ones dissolve in water? Oh, the ones that are polar will dissolve in water. The ones that are nonpolar will dissolve in gasoline. So this will be good practice if we got to remember, we got to draw the Lewis structure, look at the molecular geometry, determine if it's polar or nonpolar.
So I'm like really good at that, but could you maybe?
I sure can. All right, so which one do you want to do? NH3? Or should we try a harder one?
Oh, yeah, there's one more.
We can do NH3. Let's do NH3 and then a hard one. How's that? So we got to draw the Lewis structure. What do we got to do to draw the Lewis structure again? Count the valence electrons. So nitrogen has 5, hydrogen has 1, but there's 3 of them. So that's a total of 8 electrons. Which one's the essential atom? Nitrogen or hydrogen? Never hydrogen, right? So there's 3 hydrogens bonded to it because of this guy right there. 2, 4, 6. We have 2 more. They go right there so that they all have an octet. Good? Can we stop there, guys? Why can we? Because there's a lone pair. That's going to make it not symmetrical. So it is what? Polar. Therefore, it's going to dissolve in H2O. Good? Now, if there wasn't a lone pair, then we would have to draw the molecular geometry of it. Right? Then determine if the bond is polar or not. So H and N. So N is 3 and H is 2.1. So it's 0.9 difference. So it is polar. So this is partial positive, partial positive, partial positive, and partial negative. Can we draw a straight line that separates? Whoa. We can draw a straight line that separates the positives from the negatives, therefore it's polar. Good? Is that the only way? Just do the straight line test? We could talk about the vector dipoles and stuff, but I find most people like this better. Anybody want the vector stuff? Okay. Okay, you want to try a different one? Yeah, this big long one. CH3OCH3. Ugh. Do you remember these organic compounds? How I told you that these ones are kind of a little easier to draw the structure because it's already written in structure form. I got a carbon. We got 3 hydrogens. Then it's hooked to an oxygen, hooked to another carbon with 3 hydrogens. Do you see how that's written like this? Okay, for those organic molecules with a bunch of carbons, hydrogens, and whatever else, those are a little bit easier to draw the structure, but now we still have to count valence electrons, right? And if we do, we're going to have 2 more right there and there. Okay? Which one's the central atom, guys? Looks like that one is, right? Right smack in the middle. So is this polar or non-polar? Polar because it's in a bent form, right? Because you got 2 lone pairs and it's going to be bent. You got the negative on this side and the positives down here, so you can definitely draw a straight line. So it looks icky and yucky, but if you can recognize that that's and again, I'm not going to test you on organic compounds. I might say, well, I did on the last when we talked about this stuff, right? But yeah.
So the molecular geometry would be bent?
Yes. If we're talking about this central atom, what about this central atom?
That would be
Tetrahedral. Same with this one, right?
with the O. Or
Yeah, so if we just draw this one right here, we got this one, and we got, there's the 3 hydrogens, and then you got the oxygen and whatever else over here, right? But if we're just looking at that guy, it's tetrahedral. But when we're looking at the entire molecule, you just got to see if you can use the line test and separate the positives from the negatives. So if we draw that, we have, here's my, let's do my lone pairs right here. And then you got carbon with CH3 there and CH3 there. Do I have to worry about the carbon-hydrogen bond? No, it's non-polar. So I don't have to worry about positive and negatives with that. But the carbon-oxygen bond, this is going to be partial negative, partial positive, and we can draw a line that separates the positives from the negatives. So this is polar, therefore it's gonna dissolve in water. Yeah, Chad?
So, based on the Lewis structure, it looks like it is symmetrical because.
That's why you don't go off of the Lewis structure, yep. Yeah, you have to know what its shape is in geometric space. Good? Did that answer your question? Okay. What about LII? What do you think? Polar or non-polar? Is that going to dissolve in water or gas?
Yeah, it's an ionic compound.
Oh, this is an ionic compound,
Iodine.
and it has lithium in it, which is a group 1 ion. Therefore, it is soluble in water. It's going to dissolve in water. It's not a covalent compound, so do we draw a Lewis structure for that? Yes, we can, if you want, right? And which one is more electronegative? This guy, partial negative, partial positive. Oh, we know that's not a partial, that's a full positive, and that's a full negative, right? We can separate. We still can, right? But if you recognize that it's an ionic compound, then you got to look at your solubility chart. Okay?
That'd be the same with potassium chloride.
Yeah. Yep. Any other one of those compounds you want to do? Because this does take practice. When you get good at it, you probably won't have to draw any of these. You just look at it, yeah, yep. But you don't have to be good at it right now. Well, it'd be nice if you was, but you don't have to do it just by looking at it. Draw the picture, draw it. Yeah.
Could we do NH4 NO3?
Yep, sure can. What kind of compound is this? Ionic. There we go. This is the positive, this is negative. So what's this going to dissolve in? These are both on our always soluble ions, right? So this is going to be water.
It's just ammonium nitrate.
Yeah, so you kind of got to look at it and be familiar with your polyatomic ions so that you can just see that. Otherwise, yeah, that looks rough, right? So why you got to know your polyatomic ions? Yeah.
What about O2?
Yeah, what about O2, guys?
It's ion.
That is dissolvable.
Dissolvable in water?
Yeah.
If you add pressure, it is.
Yes.
That's how fish live, right?
Yeah, I just knew that one.
Okay.
Plants.
Okay.
This one, NH4 also.
But what would the answer be on this worksheet? Why? Oxygen is a polar molecule or a non-polar molecule? Non-polar, what's the difference between oxygen and oxygen? Zero. There's zero polar. It's a perfect non-polar molecule. So it's going to dissolve in gasoline more than water. Can it dissolve in water? Yes.
Can you help me understand what's happening in like bubbly water? 'Cause I get that the CO2 is like all over, and then does the CO2 just come together to like form the bubbles? Or am I just like way off base with this?
Well, CO2 is a gas,
Right.
and you have gas in liquid,
Yeah.
and it makes bubbles.
Right.
But, so how does it stay in there?
Well, it's just like hanging out in there, right?
Because it's pressurized. What happens if you take the lid off? It goes out, eventually it'll go flat, right?
Yeah.
So you have to have that increased pressure to keep the carbon dioxide in the liquid.
But like if I have an open cup and then I add carbon dioxide, I'm not increasing the pressure inside of the cup.
So how do you add carbon dioxide in an open cup?
Wait, I guess you can.
You can.
Whoa.
Dry ice, right?
Yeah.
You throw dry ice in there, and it starts bubbling, bubbling, bubbling. Anyway, it'll make it carbonated, but as soon as that dry ice is gone, then it'll start to just go out, right? Does that help?
No.
No, what's your question?
I don't know, like I understand everything I think I need to, I'm just confused about this, like gas and liquid. I've never understood it, I just understand it happens.
It kind of just forces it to go inside. So there's a vapor pressure, your vapor pressure it's kind of like, think about when you boil water, right? So water, the vapor pressure kind of matches and it's in equilibrium. Then you heat it, and it starts turning those water molecules into gas, right?
Mhm.
But then you see the bubbles coming up, right? That's the gaseous water that's coming up, but it doesn't go out of the water until it reaches a certain temperature to where it overcomes the atmospheric pressure.
That makes sense. Yeah, I have one, that's like what I'm thinking of.
The what?
A soda stream? Like you take just regular water and it's got a carbon
Yeah, it's
dioxide
really like,
canister and it forces
Yeah.
into the water under pressure
Yep. You got to increase the pressure
to
to
make
keep it in there.
fizzy water.
Yeah.
yeah, that's exactly what I was thinking.
Yep. That's all you're doing. You're increasing the pressure. Yeah.
Did you do CH2, Cl2?
Yeah. CH2Cl2. Draw the structure. It's going to look something like this, right? Does it matter where you put the H's and the Cl's? No, it doesn't. But we can't do it like that. We have to put it in molecular geometry, right? So it's going to be C. Where do you want to put the H's? It really doesn't matter. Okay, so right here. And you put this guy right here and that right there. Do we have to worry about the carbon-hydrogen bond for polarity? No, because it's not polar. But the carbon-chlorine bond, chlorine is 3, 2.5, so barely polar, right? But it is. So this is partial positive, partial negative, partial negative. This is going to dissolve in water because it's polar.
So we don't necessarily have to determine the amount of valence electrons and draw like the perfect Lewis structure or anything.
So why didn't I do this is what you're wondering?
Yeah.
Yeah. Do we need those to determine the molecular geometry? No, we don't. But for this class, we keep it simple. If you were to go into 1210, then you'd have to worry about 5 regions and 6 regions of electrons. And then you have to make sure, well, do you have a 6 region or a 5 region molecule? Because if you have extra electrons, then you might have to put some right there. You won't ever with carbon, but yes, those electrons make a big deal. But for this class, we're going to keep it straight, forward, and simple. Good? You can kind of just mentally put the extra electrons, right? Okay, that's where they are. Yeah, they all have an octet. Just make sure they do. Make sure it's good, and then determine the molecular geometry. Good. Anything else on this section?
Can we do CH3OH?
CH3OH? What do you think? Is it polar or non-polar?
Polar.
Why?
Oxygen.
Because it has oxygen in it. But look, you don't have to be able to just look at this and say, yep, I know because of that. Let's say, there's too much stuff to know, and you just, right? Okay, so let's just draw it out. So carbon has 4, hydrogen has 1 times 3, so that's 3, plus oxygen has 6, plus this hydrogen has 1, so we have a total of 14 electrons, right? So we say carbon's the central atom, 1, 2, 3. And again, it puts it in the structure, it writes it the way that it's structured. And we have the oxygen and another hydrogen. We count those electrons, 2, 4, 6, 8, 10. We have 4 more, 2, 4.
Dissolve in water.
So if we look at carbon as our central atom, is it polar? Yes. If we look at oxygen as our central atom, is it polar? Yes. So either one will tell us this. Even on that last molecule, either one would tell us that. Do you want me to draw the molecular geometry?
Yeah.
All right. So it's real similar to the other one we did. But you have carbon, and you have hydrogen here, and let's put another hydrogen right here. And then this is oxygen. We can stop there if you want. We can just say this is OH. Right? And not worry about this because this is our central atom. Then we look, okay, this part is nonpolar. But this bond right here is a polar bond, so this is partial negative, partial positive, and we can draw a straight line separating the positives from the negatives. So this is polar, therefore it dissolves in water. Make sense? Anything else? Is this making sense to everybody? All right. There's our break. If you still have more questions after break, we can definitely go over them. All right, we have everybody back? Almost.
Going to study new material or
It's new material. Yep. All right, let's go ahead and get started again. Any questions on solutions? What they are, how to determine solutes. Maybe we should do a few of those. If we have let's say we have soda.
the example.
Yep, these are examples. What's the solute and what's the solvent?
Water is the solvent.
Water's the solvent, good. It's the majority of it. It's the stuff that dissolves everything else. And water is the universal solvent we talked about. And then what's dissolved in there? Sugar.
Corn syrup.
Carbon dioxide. Yeah, all kinds of stuff. If you look on the label, there's tons of junk in there, right?
Yeah.
All right. Flavor, whatever. Okay? What about salt water?
There are still carbon, hydrogen, oxygen. Why it's CHEM?
What?
They're all carbons, oxygen, hydrogen, sugar.
Yeah. That's right. So salt water. What's the solvent? water. And solute is NaCl, right? We good? Do we need to go over some more? What about Kool-Aid?
Salt,
What's the solvent? Still water, unless you make it out of milk. Okay. Just anybody try that before? How did someone say, is that extra credit if you know? Okay.
I mean, I'll try it.
And then of course we got sugar and flavoring, right? Same thing.
Well, okay, wait, let's say you did use
What
milk
is it?
though. Wouldn't water still be the solvent and then you have all the milk?
If you have 1%. No, I was kidding. Or skim milk. No, I just kidding.
what is, it's killer, it's salt water and downward,
Kool-Aid.
Sugar, Kool-Aid.
cool, see, it's killer.
Okay,
Oh,
this is just punch. Okay, that's the, all right. We're good with this? All right. So just, what about steel?
That's a good
What's the majority of steel?
iron.
Iron. And then stuff that's dissolved in iron is carbon. Maybe some other things, depends on what type of steel you have, and I don't know. Maybe steel's steel. I don't know for sure. Are we good? But if you have stainless steel, there might be chromium in there, right? Or something to make it shiny. All right, any questions on solutions? All right, let's move on to concentrations. Okay, we talked about this word a few times as if we all know what it means. Do we all know what it means?
I mean, I have like an idea, but I don't have a
Good.
chemistry definition.
And that is 100% okay. Your own wording is way better than the book definition most of the time. Okay? So what's a good definition for concentration in your own words?
Percent of something in a solution.
Kind of like the percent of something in a solution, right? Okay? How much of the what? Solute you have in compared to the whole thing. If we're talking about percent, well, it's always over the total, right? And so that's basically what it is. Let me give you the equation for concentration. Now, there's a lot of different units we're going to go over, but concentration, there's only one equation for it. Amount of solute divided by the amount of solution. So this is what we're interested in, our interest, and this is the total. Sometimes when I get to the edge, it kind of breaks up a little. Maybe it's because of this. Yeah, sorry. Wonder why it does that. It used to not do that. Okay.
Sorry, what does that say?
Yeah, I don't know what it says either. Let's write it again.
yes,
Interest over the total. The solution is everything, right? And what we're interested in, how much solute is dissolved in it. Has a higher concentration if you have more solute in it, right? Kind of like concentrated orange juice. You guys ever have that at home? And you go and sneak a little bit every once in a while?
Yeah, man, it's
No?
a couple of things.
Oh yeah. Okay. Get a rush. Okay. So this is the equation for concentration no matter what unit of concentration we're dealing with. And then to change the units, you just use what? dimensional analysis. That's it, okay? Are we good here with the definition of concentration? Doesn't look like a definition, but I think this is more useful than a definition. But that's me. Anybody need the words? I'm not gonna give you a test on. Give me the word definition for concentration. Okay. All right. So let's go on to the different units of concentration. The main one we use in chemistry is called molarity. And molarity is still the amount of solute over the amount of solution, but we say it's the number of moles of solute over the liters of solution. So the symbol we use for molarity is capital M. Don't get that confused with mega. Is it easy to get that confused with mega? It's not, because mega is a prefix, right? This is just one symbol by itself. So molarity is capital M, and that is moles over liter. Has to be moles on top, and it has to be liters on bottom. Don't use milliliters. Don't use centimeters cubed. Don't use gallons. It has to be liters. Good? So what if we can't measure moles? Oh, yeah, we can't. We know grams, right? What if we have the amount of grams we have in milliliters? Can we convert that to moles per liter? Yeah, convert grams to moles, milliliters to liters, and then divide the two. That's it. Okay? So let's do should do an easy example or a more complex example? Easy? Yeah, stick easy. And then we'll do a hard one later. Okay? All right, so calculate the molarity of 0.034 moles of HCl in 1.5 liters of HCl acid, hydrochloric acid. In 1.5 liters of HCl.
Is it HCl?
What?
1.5 liter of HCl acid?
What? So, yeah, 1.5 liters of HCl acid. Yep. Okay, so how do we calculate molarity? Moles of solute. Oh, which is the solute? The acid or the HCl? Acid is an aqueous solution. That's how we know it's an acid. Did we talk about that? With acid-base reactions? Acids and bases must be aqueous solutions. That means a solution where water is the solvent. Okay? So this is the solution. This is the solute. Good? So 0.034 moles of HCl over 1.5 liters of solution. And we do the math, we get 0.023. We can call it moles per liter, or we can just say 0.023 molar solution of HCl. You see how I changed the name a little bit? I call it 0.023 molar solution. Means the molarity is 0.023. Good? If we want to go to another unit, which one's better? 1 or 2? 1. It tells us what the units are, then we can convert what we need to. You follow? So if we're going to use it as a conversion factor, use it as moles over liters rather than capital M. Yeah?
Is molarity the only unit of concentration that will be used?
No. Nope, we're gonna do 1, 2, 3, 4, 5, 6, 7, 8. Maybe not today, but we'll get to 8 by next time. Okay?
I thought you were pulling our legs for a second, like 9, 10.
No? I think just 8, we'll see. But really, this is what it is. That's how you calculate them. Okay? Are we good with molarity so far? Okay. Should we try a harder one? Oh, that's just a divide problem, right? Plug and chug, we're good. Okay, so let's see. Let's say we have 35 grams of sodium chloride, and we want to make 250 milliliters of salt water. What is the molarity? We can do this a couple of different ways. Who likes to do it in one big, long problem? Who hates doing it that way? Okay, let's do it, break it up one step at a time, and then I'll show you one big, huge problem. Okay, here we go. So, we have grams of, which one's our solute, guys? Yeah, this is our solute, and salt water is our solution. Concentration is solute over solution, right? Okay. What does solute have to be for molarity? Moles. So we got to convert this into moles, and we got to convert this into liters. So we can convert one at a time, no big deal. 35 grams of NaCl. How do we convert grams to moles? Molar mass of NaCl. You don't have to memorize this. I just done it over and over and over again to where I remember. Did I remember right? Make sure I did. Sometimes I remember wrong, right?
58.
And that's grams. What?
Yeah, you got it.
Yeah. And so that's equal to something. I didn't do it this way. Actually, yes, I did. 0.0599 moles of NaCl. We get so far? Okay, then we got to convert 250 milliliters into liters. Some of us can do this in our head, and that's okay. Convert milliliters, what goes on bottom? Yeah.
Is it 0.599 or
0.0599. That's what I got. Did you get 0.599? Oh, did I make a mistake? Oh, I probably did. Okay. All right, so how do we convert? Thank you for catching. How do you convert 250 milliliters to liters? What goes on bottom? 1,000 milliliters to 1 liter. That goes away, and we're left with 0.25 liters. Now, how do you find molarity? You just divide those two, right? Moles of solute over liters of solution, and we should get 0.24 molar solution of HCl, of NaCl. Is that what we're getting? Ah,
What we do the
no?
2.396.
2.396? Then, let's check. Oh, that's why. I did it right. In my notes, I wrote 3.5 grams. My bad. Okay. We'll stick with this one. Good. That means my notes are still good. All right. So we got 2 point what? .396 rounds to 4. 2.4 molar solution of NaCl.
How did you divide it by 0.25?
Yeah. So concentration in molarity is moles of solute divided by liters of solution. Make sense? Yeah, Andrew.
I know you said you like to keep things simple, but I can also foresee maybe a question asking like the solvent instead of solution. Do you ever do that? Like if we said 35.
In my 1210 class, that was done, and a lot of people got it wrong.
Okay.
Okay. But yeah, it has to be solution on the bottom.
Okay.
What if I have 10 grams of solute and 30 grams of solvent? How many grams of solution do we have?
40.
You add those together, right?
Just making sure.
But
We'll see that or not.
I don't, yeah, I won't do that. In 1210, we try to trick you. Okay. All right. I mean, if you think about it, you have to know what you're doing. You really do. You have to know your units, and you have to know you're not just, oh yeah, it's supposed to just divide them. In class, teacher says just divide, right? And that's what we do in elementary school. So, teacher, do we times or do we divide? Isn't that how we do it? But when you get into your career, you have to know what you're doing. Otherwise, you're going to make mistakes, right? So, in a way, I see why we throw those at you, but I don't know that we do in this class.
I guess I was just thinking like how it's worded also throws me off. Like, oh, if we're trying to make 250 milliliters of salt water, like.
Yeah. Well, if I have 35 grams of salt and I want to make 200, well, this is going to be hard. It's probably not going to dissolve all the way if I use 35 grams. It was supposed to be 3.5 grams, but okay. That's quite concentrated, but okay. But it's still the correct way to do it. Good? Yeah, Alex.
Semi-related question. I've tried to dissolve as much sugar as in like a can of soda into 12 ounces of water, and I couldn't do it. So like, how do they do it?
Yeah, how do you think?
Do they like heat it up a lot?
Heat it
before
up.
they can?
Yep.
But then how does it not?
Has it not become super saturated, and then you just throw another crystal in there and it
It's
crystallizes?
just like pressurized in a can, right?
Yeah, it is, but if you let it out, it still doesn't come out of solution.
Yeah, and like all the sugar doesn't congeal.
Great question. So with sodium acetate, the one where you get a supersaturated solution, so everything won't do that. But sodium acetate will, because it is a salt, so it dissociates, and then if there's too much of it, it'll come back. Okay, and when it comes back, it kind of creates that crystalline structure, and then it kind of just goes kind of just. But for salt, but for sugar, it's not an ionic compound. It's just there.
Yeah.
But if you can get it to dissolve, like increase the temperature or pressure, it'll dissolve and it'll stay dissolved.
Okay. That makes more sense.
Good? All right. So you ready for the one problem done? Okay. So concentration is the amount of solute, which is 35 grams, not 9, over the amount of solution, which is 250 milliliters. That's concentration, end of story. But now we're not in the right units, right? So now we just do what we did here and do 1 mole. You didn't see that, did you? 1 mole of NaCl to 58.544 grams of NaCl, right? And we can see grams cancel out. So far, so good. And then we do 1,000 milliliters to 1 liter. That goes away. And now we're left with moles per liter, and we're still going to get the exact same number. I kind of made this way sound scary, didn't I? One big, huge, long. So which one takes less space? Which one should you use? Whatever one you like. Okay?
1,000 milliliter.
Yeah. Are we good there? Now, sometimes you use molarity just as a conversion factor. And we're going to do that quite a bit in next unit, in chapter 10. So if I have, let's say, 250 milliliters of a 0.5 molar concentration of HCl, can I figure out how many grams of HCl are in that? Right? So we have two things that we know, and we know what we don't know. We know what we're looking for. So where do we start? With what we know. We know two things, so which one should we start with? Doesn't matter. Which one would you start with? Why that one? This is milliliters, and this is what? Moles over liters. That's 2 units. But it really doesn't matter. Okay? So we have 250 milliliters. Can we put that into the dimensional analysis yet? No, because this is moles over liters. We need to convert this to liters first, right? So we got 1,000 milliliters to 1 liter. Are you guys following me, or am I just doing this? Good? So milliliters goes away. And now we have liters, so do we put 0.5 on top or 0.5 on bottom?
Top.
On top, so 0.5 moles of HCl per 1 liter of solution, because this is right here, it means 0.5 molar, right? Does that make sense? So liters goes away, we're left with moles. Are we there yet? No, we got to keep going because we got to go to grams. So 1 mole of HCl goes on bottom so that it can cancel. And the molar mass of this is 36.45 grams. And there we go. It's just a conversion problem. We good at dimensional analysis yet? Because if we're not, chapter 10's really going to hurt. We got a lot of that going on. Okay? A lot of stoichiometry, a lot of dimensional analysis.
Where do you get 36?
This is just the molar mass of HCl.
You divide 0.5 over 1,000.
250 divided by 1,000
No, 250 divided by 1,000
times 0.5,
0.5 get 36.
and then multiply 36.45. And we get an answer, right? What's that? Yeah, so our answers, our answer is going to be measured in grams of HCl because that's the only unit we have left. Are we good?
So it's equal to 45 grams of HCl.
What?
It's equal to 36.45.
Yeah, 36.45 grams per mole is the molar mass of HCl. Are we good? Okay, any questions with molarity? There's more examples on this worksheet. But do you want to do another example? Okay, I'm seeing no's. Yes? Okay. So let's, on section 2 on our worksheet, let's do the very last one on the right side, the third one down on the right side. Says we have 0.825. Let's read the instructions first. It says calculate the concentration of the following aqueous solutions in molarity. So 0.825 grams of C2H6O in 700 milliliter solution. Okay, so this tells us which one the solution is. That means this one over here is the solute. Good? Do you want to do one-dimensional analysis problem?
Yeah.
Or break it up? Okay, so we're going to start with our solute on top. Our solvent on bottom. Or sorry, our solution on bottom, not our solvent. And now what?
Molar mass.
Can we do milliliters first? Sure, it doesn't matter, it really doesn't. So I like to start with the top just because that's how we read. But yeah, so grams of C2H6O, we want to convert that to what? Moles, good. And that means we need to find the molar mass. So carbon is 12.01 times 2 is 24.02. Plus hydrogen is 1.008 times 6 is something. 6.48 or 0.48? Probably 0.48.
36.06.
0. Is that right? Okay. Plus the 16. So 30, 40, 46.07. Did I do that right? Use a calculator, guys.
46.
46. To 1 mole. Grams goes away, good. Now what? We have moles of solute on top, that's what we want. What do we want on bottom? Liters. So what goes on top? 1,000 milliliters to cancel out with milliliters to 1 liter. We have moles per liter. Tells us we're done because that's molarity. And I don't have this answer. Wait, maybe I do. $17.9? Yeah, 0.0256 molar solution of ethanol. Is that what you got? Yeah.
2 0. I got 2 zeros and then 2.002.
Maybe good. Let's have somebody else check.
Can you do it?
Because it's easy to make a little mistake in calculations. Measure twice, cut once, right?
Oh, yeah, I did the.
We good?
I did the top one, yeah.
Does this make sense to everybody? We did the hardest one on section 2. And then section 3 is a dimensional analysis one where we used molarity as a conversion factor. Do you want to do one more of those? Okay. So which one? The first one or the second one? I'm going to do one. You can do the last one on your own.
Can you do the last one?
Yeah, because that one looks icky. Kate has a big, huge, yucky thing we have to calculate molar mass, right?
The gram of
Okay, so it says we want to calculate grams of solute. And we know that we have 50 milliliters of a 0.360 molar concentration of, can anybody tell me what this is called? Okay. Potassium dichromate. Is dichromate part of your polyatomic ion? Was that one of them? But we didn't get him down yet? All right, well, get him down. All right. So what do? We know what we're looking for, and we know what we know. So where do we start? With what we know. So tell me, where do I start? 50 milliliters, great place to start. Should we start with the other one first this time? Just to show you it doesn't matter? Okay. So we're going to change this molarity into what? Moles over liters, right? 0.360 moles of potassium dichromate to 1 liter. Can I use this one yet? No, we got to go to milliliters, right? 1 liter is the same as 1,000 milliliters. Okay. I want to know grams, so I got to convert moles into grams. Do you want to do that first, or do you want to take care of this 50 milliliters? Does it matter what you do? It doesn't. Multiply 50 milliliters. Milliliters goes away. Yeah, you guys all confused on what goes on the bottom? Right? And this is why it's easier for most people to start with the most simple, because then you don't have to worry about that, right? I mean, if you understand it, you don't anyway, but that's where a lot of people get hung up sometimes. Okay. All right, so we hit grams yet? No, so we keep going. Molar mass of K2Cr2O7 is?
294.2.
Thank you. 294.2 grams of potassium dichromate. The moles go away, we're left with grams. That tells us we can stop. Stop converting, multiply and divide. And what do we get? .2956, 5.3
5.30
grams of potassium dichromate.
We're gonna have to figure out like partial solutions, like there's
Partial?
sugar in this and there's this much salt. Okay, cool.
Nope.
Cool.
I mean, you could though,
Right.
right? You'd say, okay, there's 3 grams of sugar, 5 grams of this, and so on, right? If you want to know what the molarity is of just sugar, then you just do sugar over solution. Yep. And normally what we do instead of molarity in this case, we do percent. That's what we're going to do next.
Yeah, I like it.
Okay? Are we good with molarity, guys? All right. So it looks like we won't finish all of these today. That's okay. So we'll do some next time. But let's try to see if we can get done with at least 3 more. Okay? Maybe 5. Because these ones are almost the same. Okay? Just slight differences. So are we good with molarity then? All right, the next one we're going to talk about is mass percent. Our concentration by mass, and it's a percentage. Are we good with calculating percentages? How do you calculate percentages in general? What we're interested in divided by the total times 100. That's it. And if we're dealing with mass, then how do we find the concentration of mass percent? What goes on top? Mass of what?
Solute.
Good. That's our interest. What goes on bottom?
Solution.
What unit? Mass of solution. Then when we're done, we do times 100%. Solution is the total, right? So the only difference is we multiply by 100%. Now the thing you have to keep in mind though is these masses better be the same unit. If one's milligrams and the other's kilograms, doesn't really work, right? They got to cancel out. What are the units of percentage? Percent. There's no grams, there's no, right? They have to cancel each other. Are we good with that? Okay, before we do an example here, I'm going to show you 2 more that's almost just like this. Okay, the next one is volume percent. Can anybody tell me the formula for the concentration of volume percent? Volume of solute over volume of solution times 100%. And what do we got to make sure? The volume's in the same unit, so they cancel out. We good with that? Pretty straightforward? All right, what about mass to volume percent? You think this is possible? Does mass ever cancel out with volume? It does only with aqueous solutions. Why is that? The density of water equals 1 gram per milliliter. 1 gram of water equals 1 milliliter of water. They cancel if we are using grams for our solute and milliliters for our solution. Does that make sense? So the equation for mass to volume percent is grams of solute over milliliters of solution times 100%. And again, this is only for aqueous solutions. Aqueous. But that's generally what we use in chemistry, right? Is aqueous solutions. There are sometimes we might not use aqueous solutions, but most of the time we do. What happens if it doesn't tell us what the solvent is?
Assume water?
Assume water. Yep.
If what?
If the problem doesn't tell us what the solvent is, assume that it's water.
aqueous solution.
And if it tells us, then it's not water. Good? Are we good with these percent concentrations? All right, let's do an example. Do y'all have that? Okay. So let's say we have 15 grams of glucose is dissolved in 100 milliliters of solution. Determine the concentration by percent. Yeah, this is going to be mass over volume. And it doesn't tell us what the solvent is, so it must be water. So what do we do? 15 grams of glucose over 100 milliliters of solution. Now what? Times 100. That's it. We're already at grams per milliliter. We don't have to convert. If we start with moles and liters, or in other words, molarity, you see how we can convert that to percentage? Okay? Yeah.
So grams per milliliter are the units for this
That-
percentage?
Well, what are the units of our percent? Those go away. Oh, why did they go away?
It's 50.
Because 1 gram of water equals 1 milliliter. They're the same
It's again
for water.
15%.
Yeah. These hundreds go away, so it's 15%. 15% glucose. We have to say what we're interested in, right? 50% what? So 15% glucose. How are we feeling about that? So you have to know what these are, but percentage is always the same. What we're interested in divided by the total times 100. What we're interested in is the solute. The total is the solution times 100. If it's mass, they better be the same unit. If it's volume, they better be the same unit. If it's mass to volume, it better be grams per milliliter for an aqueous solution. Good? And on our worksheet, there are 8 examples of these. So on section 5, it says use W to V. What does W mean? Weight. That's not exactly mass, but seems like everybody uses weight interchangeably with mass. Okay. Just so you know, if they use weight, like sometimes people say the formula weight. What's the formula weight, guys? What's another name for that? Molar mass. I like molar mass better. You can also call it formula mass, but okay. Why do I like molar mass? Because it's the mass per mole, right? Okay.
Sorry, mass and weight not the same because like you weigh less on Mount Everest than you would at sea level, but your mass would stay consistent?
That's right.
Okay.
Yep. And they're different numbers.
Right.
Yep. But, yeah, your weight changes depending on where you are, but your mass stays the same. Tell you eat a bunch of hamburgers. Okay. All right, we good? Do you want to do any other examples together, or should we kick 2 more out before we leave today? If you guys don't feel comfortable, let's practice. But definitely practice before the night's over or before the next day, okay?
Would you have an example?
What? Volume to volume? All right, let's do it. So section 5 says we have 450 milliliters of, this is just ethanol, in 1 liter of solution. So how do you find the volume to volume percent? 450 milliliters of our solute, in this case C2H6O, is that right? Yeah. Over 1 liter of solution. Should we times by 100 yet?
H4 or H?
What?
100 milliliters.
Yeah, we have to make sure there, you have a question, Aman?
Is it C2H4 or H?
C2H6. And it is whatever it is on the worksheet. And on the worksheet, they put it in structure form, and that's just a little messy. But, so we convert either milliliters to liters or liters to milliliters. It really doesn't matter. So 1,000 milliliters to 1 liter. And if you'd rather multiply, then do it the other way around, right? Everything cancels. That tells us we're doing good. Now what do we do? Times by 100%. That's it. When I say that's it, I'm not saying it's easy. Just saying that's all there is to it. So we divide that by 1,000 and we get 0.45 times 100 is 45%. Percent what? C2H6O. Good? Did that help? Come on.
Yes, the mass is the same. So it's the same.
Yeah.
The same divided.
Yeah, just make sure they're the same units so that they cancel out. If they don't cancel out, we're going to have funky units, and then it's not, the ratio is not the same, so it's not really a real percentage. We good there? Okay, we have just enough time to do 2 more. These 2 are real similar, so we'll do them together. So I said 8, but not too bad, right? We're already done with 4 of them. There might be 9. Okay. So the next one is parts per million. We're just going to abbreviate it ppm. And we got parts per billion. Is this a high concentration or a low concentration? Low, extremely low concentration. So this is what we talk about when we say, okay, there's chloride in your drinking water. What's the parts per million or parts per billion of that, right? It can be a low, low, low concentration. Otherwise, no one would ever want to drink it, right? Okay. So parts. So first of all, what I mean when I say parts. You guys ever paint your wall and you want a specific color? And so you have to mix stuff together. In fact, you just tell this to Home Depot and they'll do it for you, right? But when they do it, well, let's say you wanted to paint just the tabletop. Then what are your parts going to be? Maybe ounces, right? You're going to get 3 parts of this color to 2 parts of this color in ounces. So 3 ounces of this to 2 ounces of this, and you got it. It's got to be the same unit still, right? No difference in the percentage we just did. Have to be the same units. Okay? So parts per billion, parts per million is going to be mass or volume of solute over mass or volume of solution. Then we don't times by 100 because we're not finding percentage. We times by 1 million for parts per million. What do we times for parts per billion? 1 billion. Yeah? So just make sure these are the same units, these are the same units, so they cancel. Can you use mass to volume? If it's an aqueous solution, you can do grams per milliliter, just like before. Does that make sense to everybody? Okay. So you just want to make sure the units cancel. And our unit's going to be ppm or ppb. So what's the formula for parts per billion? Exactly the same thing. This time, we're going to do times 1 billion. What's another way to write 1 million, guys? 10 to the 6. And this is 10 to the 9. Right? And that's going to be parts per billion. So basically the same thing, just slightly different, right? Should we do an example? Yeah, let's do it. So it's still what we're interested in, divided by the total, but the units need to cancel out just like in percent. Okay, yeah, question?
It's 10.
10 to the 9, 10 to the 6. Because this 1 million is the same as 10 to the 6 power. 1 billion is the same as 10 to the 9 power. So you can do one or the other. Okay? This might be a disadvantage because then you might count wrong, right? All those zeros you have to type in. So you just write 10 to the 9 and you got it. Or you type 10 to the 9 in your calculator and you got it. All right, let's do an example. So tap water is fluorinated by adding, let's say, 32 milligrams of sodium fluoride for every 20 kilograms of tap water. Tap water. So tap water is fluorinated by adding 32 milligrams of sodium fluoride for every 20 milligrams of tap water. So what's my solute, guys?
Sodium chloride.
Yeah, the sodium fluoride. And my solution is tap water. Are we good? All right. And I want to find what it is in parts per million. Okay, tell me what to do.
Convert milligrams to grams and
Or can we just throw it in and just do one dimensional analysis problem? That better?
As long as they're the same units by the end.
Yeah. So what goes on top? 32 milligrams of NaF over 20 kilograms of tap water, or we just call this solution, right? You with me? Should we times by 1,000,000 yet? No? Let's convert. What do you want to convert first? Should we can convert milligrams into kilograms, kilograms into milligrams, or we can convert everything to grams. I think that would be the easiest, personally, but do whatever comes to you. So 1,000 milligrams to every 1 gram, and 1 kilogram is 1,000 grams. What cancels? Milligrams, kilograms, and grams. That tells us we're doing it right. Everything cancels. Now what do? Times by 1,000,000. What else cancels? All those zeros. Will it always do that? No. Okay. So really it's just 32 divide 20. And again, it won't always be that simple. You follow your units.
You have to multiply that.
And so we get 1.6 parts per million. So 32, divide 20, divide 1,000 times 1,000,000. Your calculator will do it for you. You don't have to see that they cancel.
But we have to multiply first and divide this.
Doesn't matter. Does not matter. You can multiply all the top, divide all the bottom, or you can multiply the top, get an answer. Multiply the bottom, get an answer, then divide the two. A lot of different ways, yeah.
So it's kind of like a percentage, but instead of per 100, it's per million.
Yeah. Yep. Not percent, per billion, per million, yep. What if we start with our 1.66 part per billion? Can we figure out how much solute we have? Well, this is 1.6 grams of NaF to what? What goes on bottom? One million grams of solution. Is that right? 1.6 parts per million. And then if we put it in our formula, multiply it by 1,000,000, and it goes away, and we have what? 1.6 parts per million. Good? I didn't find out how many grams, but does that make sense? Should we calculate the number of grams?
No.
You don't want to?
Well, no, sorry, I misunderstood the question. I was thinking moles for molarity.
Yeah, let's say we got to go to moles, right? To find molarity. We can convert this, can't we? Am I over? Almost. If you want to go, you can. So 1.6 parts per million, put it in the equation. That's the parts per million is equal to X number of grams of NaF over what? 1,000,000 grams of NaF of solution, rather. So how many grams of NaF do we have? Oh yeah, we got to times this by 1,000,000. Oh, yeah, it's just 1.6. 1.6 grams. Well, if we knew how much we had, we'd have to convert that, right?
When you
But-
multiply, when you divide by down and then multiply multiply again, you get 1.6.
Yeah.
What does it mean?
So it means we have 1.6 grams of NAF if we have 1,000,000 grams of tap water.
Oh,
But what if they tell us we have a certain amount of grams? Could we convert that? Dimensional analysis? Yeah, Rebecca.
How can we know when we need to, how can we know when we need to solve for ppm or ppb, like, you're gonna give it to us or we need to figure it out?
Well, let's say we do our calculation here without timesing by 1,000,000 or 1,000,000,000, and we get 0.0000000000564. What are you gonna multiply by? 1,000,000,000, right? Just so that it's a nicer number. But I think in general, I'll tell you if you're gonna convert to parts per million or parts per billion. But that's how you do it in real life. Because maybe they don't tell you what it is, right? So you have to figure it out. Good? Anything else? Okay, we took the whole time. I'll let you go a minute earlier. You're welcome.